Okay, so I'm just going to make a quick note on uniform probability, which just to make it more explicit. So if my probability space is equal to E1 through EK, and the probability of the set E1 equal to the probability of the set E2 equal to the probability of the set EK is equal to 1 over K, then this is what it means for it to be a uniform probability space, that every single element of omega has an equal likelihood of showing up. So another way to say this is if I have S as a subset of omega, then the cardinality of S divided by the cardinality of omega is the probability of S. So to spell that out, so if you have two item, like if S is the odds of you drawing two specific cards out of a group of 7, one of two specific cards out of a group of 7 cards, then it would be 2 divided by 7. Cool. So now we're going to just look at 2 of the questions from the textbook that relate to this previous section. So what is the probability that if we were to roll a 6-sided die that we would get an even result? So the set E would be equal to 2, 4, 6, right? And a 6-sided die is a uniform probability distribution. So the probability of E is just going to be the cardinality of E divided by 6, or the cardinality of omega, which is 6-sided die, so 6. So that's 3 over 6, which we normally write as 1/2. If I'm looking at the probability of a multiple of 3 coming up, then I would have P of T is equal to the cardinality of T divided by 6 is equal to 2 over 6, which we normally write as 1/3. So pretty straightforward there. Now, prove that for any 2 events, the probability of the intersection of A and B plus the probability of the union of A and B is equal to the probability of A plus the probability of B. Sometimes you'll see this written as A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. And if you look at this on a Venn diagram, this way makes a lot of sense, right? So that the probability of A represents this whole area right here, and the probability of B represents this whole area right here, and then I'm just double counting this middle ground. And I don't want to double count that, so I would subtract it out. But we can give a kind of a rigorous set theoretic proof for this, which is what we'll offer right now. So the probability of A can be written as the probability of A minus the intersection of A and B plus the probability of the intersection of A and B. Right? So this just follows from the fact that the intersection of these 2 is empty, right? So the probability of that is going to be 0. Actually, I should lemma here. Probability of the null set is O is equal to 0. I'm going to prove that right after this. I'm going to use that right now. So the intersection of these guys is empty. So I can use axiom 3 to add them up. So is that axiom 3 or is that, which axiom is that? Yeah, it's gonna come from axiom 3. So the probability of B is also going to be look more or less the same, plus the probability of A intersect B. And then I can add these guys together, therefore, so P of A plus P of B is equal to the probability of A minus the intersection of A and B plus the probability of B minus the intersection of A and B plus 2 times the probability of A intersect B. So I'm going to redraw this Venn diagram down here to make sure you guys see something for a second. So this whole area is A union B. This right here is this set. This right here is this set. And then we have the intersection. So that's one of these guys. So the A union B is going to be equal to A minus A intersect B plus, union B minus A intersect B union A intersect B. Cool. So I'm going to use this to say that probability of A intersect B and the fact that each of these guys is mutually exclusive, so I can just add them up. So probability of A intersect plus the probability of B minus the intersection plus the probability of the intersection. So this guy, so then substituting in up here, we would get P of A plus B is going to be equal to P of A union B, plus I still have the second one of these, so plus P of A intersect B. So that's what we were trying to prove. And now let me just prove that the probability of the null set is always equal to 0. So the probability of the null set is equal to 0 because the probability of the null set is greater than or equal to 0 by axiom 1. And now assume for contradiction that that probability of the null set is strictly greater than 0. If I do that, then that means there exists a k in the integers such that the probability of the null set is greater than 1 over k. And then I can just use axiom 3 so the intersection of the null set with the null set is equal to the null set, so they're mutually exclusive. So I can apply axiom 3 to say the sum of the probability of the null set from I equals 1 to k plus 1 is greater than 1, which would mean that the probability of the null set is greater than 1. But that's a clear contradiction, because the probability of omega has to be greater than the probability of the null set. And this guy is equal to 1. So therefore, we have a contradiction. Contradiction. Cool.